Okay, all right, so here's what we have today. We're going to go through a couple notes on the different types of polyhedra today. We're just going to take some notes. That's it, nothing else. I think it's pretty straightforward. So if you have your notes set, it should be more than fine. Let's see. Oh, I have okay. Okay, so here's kind of our idea. Now, for you guys who've been last Friday, we introduced this, right? Last Friday. Now, if you're gone, you're absent, you had something else going on, you're going to miss these notes, and now you're going to scramble them all, you got to get them down. Today's goal is just to go through a couple review, some of the vocab we introduced Friday, and then go about three new slides that introduce a couple new words. Okay, so our big focus is on prisms and pyramids today, and then we'll get to the formulas. So that's kind of my three new slides I want to talk about. But yeah, so pretty straightforward. We're not getting any homework like that today. It's a Monday, and we keep it kind of light today. I just want to do a few notes. We'll look at probably homework tomorrow, possibly. Okay. All right. Questions at all about what we're doing the next couple of days here? Perfect. All right. Let's jump right in. Let's talk about these three-dimensional figures again. We introduced this on Friday. So the main part here are outline. I want to do quick review. Now again, you already have these notes, so you shouldn't be like scrambling to write this down unless you're gone this Friday. We did the polyhedron or polyhedra, right? That's plural, it's polyhedra. The different shapes. We talked about faces, edges, and a vertex of each of them. Now on that same slide, there was something about regular polyhedra. I'm going to skip that today because it's on the next slide anyway, so I'll just jump right to it. So those, we're going to go through the definitions of these one more time so you know what the words mean, in case I start using them and you don't remember what I talked about. Number two, the second thing I want to discuss today is I want to go through prisms and pyramids. That's our main goal today. Do you understand how they name it? Do you know why they call it that? That type of thing. So prisms and pyramids. I will do a quick review of the pyramid talk that we did, I think last Tuesday or Monday. We did a lot of the pyramid stuff. I'm going to review that one more time. We'll go through the regular polyhedra or platonic solids one more time. But the one thing I want to make sure of is, do we know the curves, right? The non-polyhedra. Cylinders, cones, spheres. Do you understand what they are? Do you know what they look like? Why do they call them that? That type of thing. And then the regular polyhedra or platonic solids. Okay, questions with any of the stuff we talked about last week? I think we got up to that point. I think we ended with sphere on Friday, if you were here. The other thing that I want to make sure that we discuss today, this will be the last slide today. I want to talk about surface area and volume today and introduce those formulas. There is a lot of formula. I'm going to put that form on the board today, and your goal at the very end of class today is just to get it copied down. We're not going to do any examples of it today. I just want you to get those written down so tomorrow we can jump right in and talk about what all those formulas mean. Okay, questions at all? Perfect. All right, let's jump right in. Okay, so polyhedra, definition, or polyhedron, right? So the main definition here, it is a three-dimensional object that uses straight faces, like straight edges, and they enclose a single area of space, single region of space. So here you go. Flat surfaces closing a single region. This room would be considered a polyhedron. Okay? Single region. Now, polyhedra is plural. Hedron is singular. Now, the parts of a polyhedron. So if we looked at the picture from last Friday, again, you already have these notes. But the faces are the actual walls. Okay? So the actual walls are polyhedrons, right? Or faces, sorry. So like the floor in this room would be a face, this wall over here is a face, the ceiling is a face, you get the idea. They're actually flat surfaces. Now, where those faces meet, those are called edges. It's an actual line of the actual shape itself. It's a segment. They have to be straight. There's no curves to it. And then the vertex is where all those edges would meet. Now, here's the definitions one more time. Face is a flat surface. Edge is where those surfaces intersect. And vertex is where the edges meet. Now, on this picture I just provided you here, sometimes some people call like that bottom, they call this bottom part a base, right? So the idea is that on this base, on this part right here, it can be known as a face. It's the same thing. It doesn't matter that it's sitting on it. It's a part of that object, so it can be a face or a base. Now, why I bring this up is because if you look at both these pictures here, these two, the pictures have different styles of bases, right? This one actually has two different bases, depending on which way it's sitting, and this bottom down here has one base. The idea is that that's how you name it. So the naming system for pyramids and a prism is based on what those bases are called, okay? So we're going to get to that in a minute. All right, questions on the naming systems that we're going to get to today? Perfect. Okay, let's jump right in. I'm going to talk about the regular polyhedra. These are like those special ones, like tetrahedron, hexahedron. Let's go through those one more time. If you're not here Friday, we'll get to that. This regular polyhedra definition is on the next slide, so I'm going to go to it right away. All right, regular polyhedra. The same definition in the last slide. Here it is. It is a polyhedra where all the faces of this figure are congruent regular polygons. Congruent regular polygons. They're all the exact same polygon and they're all perfectly regular. Regular definition, they're the same edges and same angles. Like everything, they're perfect shapes. Like a equilateral triangle is a perfect polygon, it's a regular polygon. A square is a regular quad, right? But these shapes are made of just those objects. So 5 types. Number 1 is called a tetrahedron. It is a triangular pyramid, but it's made of equilateral triangles. So here it is. This is a perfect pyramid. The base is an equilateral triangle, and all the walls are equilateral triangles, and they're all the exact same triangle. Okay, that's 4-sided though. Now the next one is called a hexahedron. It has 6 sides. They're all perfect squares. It looks like a dice, if you will, a cube. So it's just, when you see it, like they're just like perfect images. I know that cube doesn't show it, but all the walls are exactly the same dimensions. Everything. The next one is an octahedron. 8 sides, 8 perfect triangles. I think we even talked about, games that use this shape last Friday. Because gaming systems use these shapes for objects because they're the easiest things to program. You don't have to adjust numbers. They're just all the exact same digits. So it's pretty easy. Next one is a dodecahedron. 12 sides, 12 perfect pentagons on this shape. It's the pentagon. It's a princess cut diamond. So you're looking top down. Pentagon top, bottom. The one side has 5 pentagons. Then when you flip it over, it's got 5 again. And then icosahedron. It's got 20 perfect triangles. I can't even explain how to look at that thing. It's just the Scattergories die. That's how I think of it. Okay, questions at all about the different shapes? Now we had those last week. These are perfect. Not every shape, is going to be a platonic solid. These are just the perfect ones that they would fall any face down or up depending on how you roll it. Okay. Now, when most people think of the shapes, they think of the prisms and pyramids. So a prism, by definition, the definition of a prism, it has 2 parallel polygons. Parallel means that they're going together, they're not intersecting. They're parallel to each other, they're the same shape, and they're connected with rectangles. So it is 2 parallel congruent faces, they're called bases, and they're connected with rectangles. So here's a shape. Now, when you name a prism, here's the naming system. You have to look at the walls that are parallel to each other, and that's the name of the shape. So in this case, the bases on this particular shape are pentagons. So this is called a pentagonal prism. The 2 walls that are parallel. The next slide will have a bunch of different examples of it. So you can see different shapes and how to name them. The next one is called a pyramid. A pyramid has some type of polygon for a base, and then perfect triangle faces that go up to a singular point, the singularity. So on this one, this has a rectangle, so it's a rectangle pyramid, a rectangular pyramid, square pyramid, if you will. But again, the faces are all triangles going up. Again, these shapes are not regular. I don't care that all these triangles are equilateral on this particular shape. They don't have, this isn't regular because the bottom isn't the same shape. The bottom is a square. You can't mix and match to make regular. Okay, do we understand the 2 names though? That one's called a rectangular pyramid. Okay. All right, next. The next types are the non-polyhedra, so the curves. One is called a cylinder. A cylinder has two parallel circles, kind of like a prism, right? They're parallel, and then it's got a curved surface that connects them. Well, here's the thing. The cylinder has more in common with a prism than anything else, because you have two parallel bases, right, or circles, and the actual wall connecting them as a curve is actually a rectangle. It just bent around it. If you don't believe me, if you cut off the top and bottom to a pop can, and you cut down the side of a pop can and lay it out, it is a perfect rectangle. So it is just like a prism. There is rectangles connecting parallel walls. It just happens to be one rectangle. Now, a cone has a circle for base, a curved edge that goes up to a singularity, a single point. And then a sphere is the set of all points that are equidistant from a central location. Now, here's the weird thing. Planet Earth, and I'm not in the crazy camp talking about flat Earth people. Earth itself is not a perfect sphere. It isn't. It's elongated kind of like a football. It sits on the plane, a disk with the sun and all the other planets. And so the Earth is actually being elongated just a hair. Now I'm really exaggerating the picture. You have the equator, and then you have the prime meridian. I really stretch it out. But the idea is that the prime meridian is actually a shorter distance around than the equator. It's off by like 20 miles or so. And that's why when you take like an airplane flight from like the US to Europe, they don't go just directly east. You know, they actually travel north. They go through Greenland, Iceland, the United Kingdom, and then go to Europe. Because the distance going north, like this direction, is actually shorter than just going directly east to Europe. Because we're actually shortened. It's actually just a hair shorter. So it actually does save time. It's one of those weird things you don't really think about until you see it put into action. All right, questions on the basic shapes then? Perfect. All right, now that was the slide we ended on. This is a brand new slide. I want to go through the names of the different types of polyhedra. Okay? Okay, so the different names. Number one, if we're going to call it by a prism, okay, you would look at the two parallel bases. So here's a picture of a triangular prism, right? The two parallel walls are triangles, and then there's only rectangles connecting them. Now I know on this picture it looks like the bottom, the base is a rectangle. I don't know how you see this thing. I see it as like, it looks like a tent that's coming out at you this direction. Some people see it as it's a block coming this way. I don't know how you see it. I see it both ways. But the two parallel walls are triangles, so it's a triangular prism. Rectangles connect it. It is not a pyramid. Pyramids go up to a single point. This thing has rectangles connecting the walls. Now, you could have other types of prisms, right? You could have a rectangular prism, kind of like a shoebox, okay? Where you have the bottom is a rectangle, the top's a rectangle, you have perfect rectangles connecting them. That is a rectangular prism. You could have a pentagonal prism, where the top and bottom are pentagons, and they go up. The weird thing, like a pentagonal, because some people are like, how do you get a pentagon? I'm thinking of like the Russell Stover's candy box. You ever seen one of those?
No.
Where they're like circular. They have a bunch of different faces, and you pick up that big thing and there's candy on the inside. It's some type of prism. I just don't know how many walls there are. Maybe I'll break it in sometime. But those are like the different shapes, right? I could go more. I just gave you a select few examples. I could go like octagonal prisms and dodecagonal prisms. Just kind of weird ones. Now, for pyramids, they have the same idea. You name it by whatever the base is. Now on a pyramid, there's no parallel one. So it's just whatever the base is. So if I had a triangular pyramid, kind of like a tetrahedron, you'd have a triangle for the base, and then you have triangles going up. And the same thing you have to watch. My laser pointer's like ricocheting off the board. Don't get you right in the face. Yeah, it does it all the time. I'm just worried I'm going to hit you at some point wherever I stand. So a triangular pyramid's got a triangle for a base, triangles going up to a singularity. If I go to a rectangular pyramid, it's got a rectangle for a base, and it goes up to a point, right? Triangle faces. The rectangle pyramid is what most people think of as like the Great Pyramids. The pyramids in Egypt are not triangle pyramids; they're square pyramids. So they held up way better. It's for design. Then, there's other ones like pentagonal pyramids, where the bottom's a pentagon and it goes up to a point. That looks kind of like a teepee, or like a golf pencil. If you've ever seen a golf pencil, they have like a certain number of faces that are shaped. That kind of a thing. All right. Questions on how we name like the different pyramids or prisms. Again, this is just random examples. There's tons more. I just picked a couple out of the book. I like the picture of them, so I just put them on a slide. All right, what else you got? You got any questions on any of these? Do you want to see any other, and I can attempt to draw one if you need to. You feel comfortable with these stuff? Okay, now, one of the things I want to talk about was the pyramid stuff. Last week, we discussed the square pyramids, like the Great Pyramid of Giza. I did it like on a Tuesday on like kind of a whim. I'm going to bring that back up because some people may not have been here to see that. I'll just go through, it's like a slide, and then we'll get to the finish where we do all the formulas for volume and area. But again, these are how we name pyramids and prisms. Okay. All right, let's go to the pyramid stuff. So, Great Pyramid of Giza. It is a square pyramid, right? It's perfectly square on the base. It has 9-degree angles. Mathematically, it's impressive. It's tall, it's really big. Each of these blocks are 2 tons, so it's deceiving how big it is. The door frame's up here if you can see it. But yeah, so when you walk in the pyramid, you can go up to the grand gallery, you go down to the burial chambers for the queen. It's one of those things like, I think there's some weird silly number where they say like inside the pyramid they've only used like 1 or 2% of the space inside of a pyramid. All the other spaces are brick. But recent studies in the past year or two have shown that like when they did studies of the pyramid, they did infrared, or they're scanning it. They found that there's a heat signature over here in this corner that looks like a doorway. It's like cooler than the rest of the pyramid, where it's like a perfect doorway. Well, they can't go in it because number one, it would affect the structural integrity or the whole entire pyramid. But number two is like you'd have to remove bricks to do it, and they don't disturb the thing. So if they could scan behind it and see what's behind it, that would be just as good. So they're doing that right now. And they've also found like above, and I'll show you a picture later, they found above the pyramid, like above the great gallery, there is another huge chamber, air chamber that's above it that they can't get to. They don't know if maybe the pyramid is rotting away from the inside because maybe rainwater is getting in and it's like decomposing on the inside, or if there's an actual chamber itself, so they're going to do a lot more scans. But yeah, we'll see that in the later ones because they're not using very much space, so there's a lot of extra room in that pyramid why they would probably make something like this. Here's the Great Pyramid again. This is the big one. This is the Pyramid of Khufu. It's the big one of the 3. You can still see the limestone at the top. Because when a sandstorm blows through, right, the top still pokes up, the top of the sandstorm itself, so it doesn't get affected. The top is made of limestone. It used to be like the whole entire pyramid was covered in limestone, and it would be like limestone's really white. So the pharaohs would do it on purpose so that it would reflect sun, and if you were to stare at the pyramid itself during the day, it would be so bright it would almost burn your retina. It'd be like looking at the sun in a mirror, and the idea is that it would keep the common people from staring at a holy place. It's kind of weird, they have a lot of like reverence for like these types of structures. So, but kind of cool concept where you can actually see the top is poking out of the sandstorm itself. Again, the 3 pyramids themselves are aligned. You can see how big they are. They're perfectly aligned north and south, east and west. There is a air chamber in each of the burial chambers that points directly to a star of Orion's belt where it's matched up with perfectly. There's lots of mathematics that's involved there. But kind of cool structures. They're 6,000-7,000 years old. Now, the Great Pyramid of Giza itself, in terms of size, compared to other structures, I think I did something like that last week. Here's the Statue of Liberty. Here's that Jesus statue in Rio de Janeiro. We have an airplane, and we have a person, so you can see a sense of scale and size. Huge objects. The inside itself, you can kind of see the air chambers where they go up to like the stars of Orion belt in each one. The Grand Gallery where they had all the gold and the burial chambers, the sub-burial chambers. but there's like a ton of space that's unaccounted for that when they do scans, it's hollow, and they can't account for what's there. So they don't know if it's decomposing slowly or if there's actually things behind the bricks that they can't get to. Or there's different entrances to different items there. Kind of cool concept. So they're doing a lot more scans recently on that. But the inside of the Grand Gallery, this is what it looks like. The bricks are so tight and put together, you can't fit a credit card in between them. And the weird part is it's not cut after the fact. These bricks were laid down, what we can tell, in a spiral pattern, that they were laid down in such a way that they would make this structure on the inside. So they didn't have to cut it later. Because each of the stones weigh like 2 tons each. Impressive, like especially when you think about like the air chambers have to line up perfectly to face a certain direction, a certain star. There's tons of mathematics that's involved there. Right? We can't replicate that. They think that these air chambers are built in such a way that it keeps it structurally sound without breaking down. It relieves just enough pressure in certain bricks. So it's impressive when you actually look at all the stuff that they put together. But yeah, so those are the things we talked about last week. I think I showed similar pictures last week. Now, the last thing I want to talk about today is surface area and volume. This is the last slide, by the way. This is stuff we're going to be going into, right? We're going to go into the shapes and talk about like the formulas. On the bottom of the slide, I'm going to have all the formulas here. I'll super zoom in on it, and these are the ones I want you to write down. But let's go through the definitions of these two words. Surface area. Surface area of a 3-dimensional object is a 2-dimensional measurement. It is, so if you look at my floor in here, you can see the number of square tiles. It's counting how many square tiles will fit on the entire surface of an object. Not just the floor, but the wall, the ceiling, everything. So they count up all the areas. So it is the 2-dimensional measurement of the surface of the object. It is the sum of all the areas of each face. So if you had the area of this wall, you'd add that to the area of the floor, this wall, the ceiling, the back wall. And now why that's important, surface area is used for paint. Right? If you're going to paint a room, you have to know the surface area. That tells you how much paint you need to buy. You wouldn't have to do it for wallpapers, kind of go on a style, but wood trim, you need dimensions for it and whatnot, but wallpapers kind of went out. Wallpaper is probably the closest thing I can explain to wallpaper is like if you're going to vinyl wrap a car. You're going to put a vinyl wrap instead of painting a car, you put like a plastic coat on top of the car that will give it a different color. People do that now. It's a lot cheaper than painting a car, and it looks kind of cool when you get them done. But yeah, surface area. Gotta know that. Volume. The definition of volume. It is a 3-dimensional measurement, and it measures the space or the region of space inside an object. Right? The amount of space. So like in this room, if I was talking about volume, I'd talk about how many desks I could fit here. A 3-dimensional object. If I was doing a barn, how many bales could I put in the barn? How much grain could I fill up, an actual silo with? That type of thing. Now, here's all the formulas you need to know. I'm going to super zoom in on this. This is the last slide. You need to write down these formulas. I'm going to super zoom in on them. Super zoom on these things. There you go. Okay, here's your formulas. Now, obviously today is just to introduce them. Now, there's a ton of different variables there, P's, B's, S's, H's. All the labels are down here. These are all the forms for like a rectangular prism, square pyramid, rectangular pyramid, cylinder, cone, sphere, that type of thing. The only dimension they don't have explained up here is on the pyramid. They don't have it labeled. There's the height of the pyramid. They have this weird slanted line on the surface. But the height of the pyramid is going from like the middle of the inside of the pyramid straight up to the point. They didn't draw it because it's really hard to see that. They have that surface one that'll help you find surface area, but they don't have the height of the object. Because you need height later on. So we'll talk about that one later. And if you notice the ones with like pyramids and cones, they have really weird formulas because they taper off. They're not a solid object, they have tapers, so they have to have fractions out front. Same with like a sphere, it rounds off, so you have to have a fraction out front to account for all the missing numbers as it rounds off. But these are the formulas. You have surface area is S's, V is volume. I'd like you to write those down. This is your last slide today. Tomorrow we'll go through a bunch of examples. I'll try to do like real numbers like this room and whatnot so it makes more sense to you, like why we're doing it. And we'll try to go through some different stuff. Tomorrow we'll definitely bring a calculator. We'll probably get homework tomorrow, but it's pretty much based on these. So, all right, well, there you go.